Jim, where are you going?
I don't know. There's not a lot of astronomy. Well, anyway, I'm gonna watch up close.
Wait a minute. I want
There's not a lot of astronomy.
I want you to finish that sentence that you started to say.
I was gonna say there's not a lot of things in astronomy. I think that are a lot of the things that I think about.
I really want you to finish it now because it sounds like you're going to say there's not a lot of interesting things in astronomy. There's not a lot of stuff in astronomy I'm interested in seeing.
No, not at all.
Up close.
That have time scales that are short enough to be terribly interesting in 2 minutes.
Welcome to Walkabout the Galaxy, the year-round astronomy podcast where the science is universal, the opinions are personal, and the trivia is, once again, topical.
Whoa. Oh,
topic?
That's me.
Top
That's
work.
me.
Top work. Got it.
We are strange, charm, top and down. Someday we'll do a charmical trivia.
Charmical.
I've done trivia once.
Well, once again, we'll do charmical. And
I did it once, too.
A downical trivia.
Downical?
Yeah. Downfall trivia. Anyway... Whoever we are also known as Josh Caldwell,
Addie Dove,
Jim Cooney,
and Audrey Martin.
Coming to you from the Walkabout studio at the University of Central Florida. Subscribe to us on Facebook, Instagram, and YouTube. You can also contact us at wtg@ucf.edu with questions, suggestions, and compliments. All other form of inquiry to wtg@ucf.edu will be automatically deleted.
Oh.
Yeah.
Oh, that's harsh.
Our stumper today is explorational. I thought we had a really fun conversation last time with the getting small.
Oh, yeah.
Downsizing.
Yeah, I've been thinking about it.
Stumper. And part of that was like, okay, where do you go, right?
Mm-hmm.
Yeah.
So just this weekend, we had what turns out to be, or will turn out to have been, the final flight of VSS Unity.
Oh, yeah.
Spaceship 2, the vehicle flown by Virgin Galactic.
That was the final flight?
So they
Supposedly,
say.
yeah. Mm-hmm.
Took 3 passengers, 1 scientist, and 2 pilots to the edge of space for, let's call it 2 minutes. It's 2 minutes above
longer.
Something.
Oh, that's true. The microgravity is longer, but you're in space
depends
for
on
like
what
2
you're
minutes,
calling, right? So 2 minutes, and it's this amazing thing, and those 3 passengers at least paid some serious ka-ching for that experience. And
there were some research payloads on board.
Right. They got to, and they also paid some less serious ka-ching, but some ka-ching. And they got to look out the windows and see the black space and a little bit of curvature of the Earth, not super high, but a little bit of the overview effect. The question is, your stumper is, if you could safely make a 2-minute visit safely, don't worry about travel time, to any place in the universe, where would it be?
Whoa. Oof. I had a comment about overview effect, but I can come back to it. Any place in the universe, 2 minutes.
2 minutes.
This is sort of like we had a question you asked. We had a stumper one time, and it was like, where would you like to observe from? Kind of like take. Yeah, I remember we had interesting.
Well, then you could.
So it's
if
a similar
you remembered
thing.
Your answer to that, then you'd
I
be
do.
all set. You would be stumped.
Maybe I want to answer something different today. Time has passed.
Maybe
I'm a different
you're
person.
A different person. Yeah.
2 minutes.
Nobody else seems to be popping up with any ideas.
2 minutes.
Either.
No damage. I would want to go to
no
like
damage, no cost.
Like the surface of the sun.
Top place. Okay, like the photosphere.
Yeah, like somewhere right near a CME, like a magnetic reconnection event, where like somewhere where there's a
gigantic,
exciting plasma overhead.
Thing.
Like maybe underneath it, under the arc of a giant plasma thing on the sun.
Because those things are giant.
They're so big,
like many times the size of Earth.
The Earth.
Yeah.
Right.
Yeah.
Like 10 times the size of the Earth.
Yeah. Yeah.
Okay.
Maybe similar, but like near but a little different, near the surface of a neutron star.
Ooh,
that's quite different,
that's
I would
cool.
say.
Yeah, it's also near a star.
And then, but also I want to like go around it.
Well, you have 2 minutes.
You know, I want to go fast, as fast as I can.
Sure.
I want to not just sit still for the 2 minutes. I want the 2 minutes to be in motion. Can I do that?
Yeah.
I'll allow it, I suppose.
All right.
So moving very fast, somewhere near the surface of a neutron star, what do you expect to see there?
I don't know.
Okay.
Just some
because you haven't
frame...
taken stellar astrophysics, probably.
Yeah, I've never taken astronomy.
You'll know at the end of next semester.
Maybe,
I know, yeah.
We'll revisit this question.
Yeah.
Yes. Maybe if you had, you would give a different answer. But
Probably.
that's okay.
I probably would.
Yeah. But then if you do this, then when you're teaching astronomy, you go, well, I went to the surface of a neutron star once. It turns out boring.
Yeah, that was a mistake.
That was a huge mistake. Jim, where are you going?
I don't know. There's not a lot of astronomy. Well, anyway, I'm gonna watch up close.
Wait a minute. I wanted
There's
you
not
to
a lot
finish
of
that
astronomy.
sentence. I want you to finish that sentence
Yeah.
that you started to say.
I was gonna say there's not a lot of things in astronomy. I think that are a lot of the things that I think
yes,
about.
I
in
really,
astronomy,
really want
Yeah.
you to finish it now because it sounds like you're going to say there's not a lot of interesting things in astronomy. There's not a lot of stuff in astronomy I'm interested in seeing.
No, not at all.
Up close.
that have time scales that are short enough to be terribly interesting in 2 minutes.
These people didn't. There was no time scale involved with their 2 minute.
No, I know.
They didn't see things changing.
You've refined
in 2
us.
minutes.
He wants to see something
I want
really
to see
dynamic.
something fun and changing. I'm going to go see a supernova up close.
That's a good
Right
one.
when
Okay,
it's
you're gonna
supernovaing.
Right when it's
You
supernova.
can
How
see
up
the
close?
moment of supernova.
I'm gonna be like 1 AU from Beetlejuice or something like. But we're gonna have to go somewhere.
What is the free fall time for the star
I feel like we've had this
once it
discussion.
starts collapsing to go down to the core and bounce?
That's a good question.
I feel like
Because I think it's more than 2 minutes.
The collapse time.
And then the question is, what part?
yeah,
'cause the
which part
supernova-
in the supernova
like,
phase?
there's
Which 2
that
minutes?
bounce. That's definitely less than 2 minutes.
Yeah.
But then, if you're 1 AU away, nothing is getting to you from that in 2 minutes.
Right.
So
Well-
what part do you really want to see,
This is a
Dr.
good
Cooney?
question. That's a good question.
It takes light 8 minutes to go an AU.
It does, but I don't care. I mean, if I'm an AU away, I don't care about the light travel time. I want to be there for the time because.
I'm just asking when. See, since you said you wanted to see it happen,
Yeah,
I want to know
which
what
bit?
yeah.
The big it.
The arrival
Yes.
of the main front.
Yes.
Okay.
Yes. I want to be.
Like, you
blown
wanna
away
have-
by the
You
shock.
want to have like
shock
maybe
wave.
10 or 20 seconds to set up.
Yeah.
Like, okay, here I am.
Yeah.
What's going on?
Yeah.
20 seconds later, and then you're just kind of like experiencing that. For
Yeah.
the next
This is the
minute
little
and a half.
boy in me who wants to see a nuke go off like up close or something like that, but bigger.
But on the
bigger.
universal scale.
Universal scale. I want to blow things up.
The
Wow.
same.
Yeah.
Okay. Well, today we'll talk about yet more surprising astrophysical discoveries,
Okay.
an out there alternative to dark matter, and much more. But first, this episode of Walkabout the Galaxy is brought to you by phonons. Get jiggy with phonons. Your journey into sound at the atomic level. Discover a whole new world of acoustics with the quantized vibrations of atoms and molecules in any solid lattice. Whether you have a 2-dimensional or 3-dimensional structure, try phonons for the transfer of energy in your condensed matter, available in both acoustic and optical form. Act now for half off special phonon deals in liquids. Phonons, the gift that keeps on giving.
The gift that keeps
That's-
on
Believe it or not,
giving.
that was a trademarked motto of something
That's gotta.
until it became just something that everybody said all the time.
Is it like Kodak or like an old picture?
I like
That's
that.
a good
Hallmark?
idea. You're on
Yeah.
you're on, huh?
Hallmark.
Oh,
No.
yes.
Yeah. I would say Audrey's a little bit more on track.
Jewelry.
No. Jim?
I got nothing.
RCA.
Record player.
Record player, you did it. I'll give you credit.
Okay, thanks.
You were definitely thinking that
like
before I
music,
said
yeah.
it. Yeah. For the
Okay.
old phonographs from like the 20s to the 50s, they were saying that-
Phonographs.
yeah,
Oh, there you go.
they're back.
Wow.
They were a thing.
Are
They're a
they?
thing again. All sorts of exciting space news this week.
So much. Like all this happened right after we recorded this episode. We hung up our microphones. That's
And
not a
then,
thing
like-
you do. And then so just like bang bang bang, space news.
Rockets started taking off.
Starship, Starliner.
Yeah.
Star.
Let's do them in
base.
order.
Nope.
Geez, I wonder why I get confused all the time.
Let's do
I
them
don't
in
know.
chronological order.
really.
Chronological order.
Starliner.
Starliner launched. Finally.
This is
It
the Boeing one.
mistakenly referred to as a rocket on NPR recently.
Oh no.
Yeah.
What is
Talk to
it?
Brendan about that.
It wasn't that NPR, but
It's not a
I know what you
rocket?
mean. It's the capsule on top of a rocket.
Starliner is the capsule. What's the rocket?
It was a
an
ULA Atlas
5, right?
5
Oh, cool.
rocket.
Okay, I know.
And that was actually when it had a bunch of problems. Yes, this is Boeing's Starliner capsule that was on top of a ULA Atlas rocket.
That's what Lucy launched on.
Yes, the rocket.
Yes.
Yep.
And Lucy is
mission.
not a rocket.
Now it is making sense.
Right.
Yeah.
Yeah. So, but there had been a bunch of delays, various reasons, Atlas reasons, Starliner reasons, but it launched with Butch and Sunny.
Right.
And
is it Sunny? It's not Sunny?
I think it's
just
Sunny.
spelled Sunny.
Sunny Williams, yeah. And she did a super awesome dance when she got up to the
I
ISS.
saw that. She was
Really?
pretty-
Spoiler alert, they went to the ISS.
They made it successfully.
It's out of the timeline sequence, but they did make it successfully.
Yeah.
There was some consternation. There's some helium leaks because helium's pretty easy to leak.
It was very concerning.
It was very concerning.
Wasn't there also
the
an issue with, like,
consternation.
And they had to
the thrusters also?
Yeah, the helium leaks were, and then there was a thruster issue, but then it was fine, and they docked, and now it was announced, I think, yesterday. So they're doing some stuff up on station. They're doing checkouts of Starliner, putting it through its paces. The real stressful thing is going to be when it comes back.
Do they
They
come
had a
back
heat
on
shield
that?
issue.
Oh, it's coming
yes.
back on this.
They had heat shield issues?
On the
I'm not
first
coming
one.
back on that.
on the first one. But not this
but
one.
not on this one.
As
And
far
they've,
as
in
everybody
theory,
knows.
fixed most of the heat shield issues.
Oh,
And they've got eyes on the heat
In
shield.
theory,
Yeah.
most?
Yeah.
When?
I mean, it came
how
back
long?
fine.
Well,
How long are they
So
up there for?
they were
Just a
nominally
week
up
or
there
two.
for like 10 days, and they were
Okay.
supposed to come back on the 14th of June, and now they're going to come back on the 18th, not because of a Starliner issue, but because there's a spacewalk planned for the 13th, and so they just want to sequence things
Yeah.
better. And so, oh no, they have to stay up on the ISS for a few more days.
That's
But there's 9 people up on the ISS right now.
Oh my
It's
god.
party time.
That
a
is
party.
pretty tough. So, if they decided they didn't want to come back on that, what's their other choice? Soyuz?
So there's currently a SpaceX capsule up there right now, but other people called dibs because
Right.
they came up in that one.
Right.
There's only a certain
Fair.
number of seats available to come home up there. I don't know if there are 9 seats if you take Starliner out of the picture, but it's fine. They got, if they looked, it's
They would sequence it.
they would figure something out.
Yeah, if there was an issue, like this was the thing that was always an issue with shuttle was like there wasn't really a way if
There's
something
nothing
happened
else
to do
you can
that.
do.
Right.
But with ISS crew complements, there's always enough vehicles to get everyone down off the ISS if like the ISS had a problem, and then like if Starliner they realized, oh god, there's an issue and we can't take it back, they would sequence them in order to bring them back differently.
Speaking of heat shield stuff,
Whew.
IFT-4
Yeah,
spaceship.
Starship.
Yeah. That
Which
was
is-
pretty cool video.
Oh yeah, I saw
SpaceX.
that. I watched it.
What company? What are you talking
SpaceX.
about? SpaceX. Okay.
SpaceX big
Biggest rocket ever.
FR,
Okay.
BFR.
It exploded at the end, right?
No.
It fell.
But it
didn't explode.
It
It did a
controlled
controlled-
touchdown in the ocean.
Oh, never. Okay, I was gonna. give you
I
a
think the
reason to care.
booster did. The booster did do a controlled touchdown, but I think then exploded.
There you go.
Ah, good.
do?
Fun.
I think so. Maybe not. Did
No,
it
we
just
saw
fall
video of
over
it.
and?
Yeah, we saw a video of it touching down.
Yeah, I thought I saw
one
extra
of
booms later.
something touched down and then went.
Yeah, that's not
Well,
exploding
that's
though.
falling.
But like as it fell, it also
I thought I saw
exploded.
some little flames.
Oh,
maybe I don't know. Anyway, maybe we should check out our sources on this. Sorry, everyone. But the booster.
yeah.
So there's a big booster, and then there's a big starship on top of a big booster, and the big booster landed, did a controlled descent, and hovered over the ocean, which is like way farther than they've been able to do before. Supposedly, that thing is supposed to like come back to the launch site
Yes.
and get caught by the tower
The chopsticks.
with chopsticks.
Yes.
Yeah.
And the announcer guys were like, "Oh, maybe I'll do it the next time." And I'm like,
That's-
I think that is a big jump because that is a lot of infrastructure. But SpaceX has demonstrated that they're
They're-
like, "We'll blow up our infrastructure.
right.
It's fine."
They're
So maybe
busy,
they'll do that.
They're busily building a second launch tower, so
Yeah.
if they blow up the first one, it's not the end of the world. Also, we have video of this. They have video of this booster touching down in the Gulf of Mexico because it came back to the spot in the Gulf of Mexico that they were aiming for, and they had
Oh, that's
anchored
nice.
a buoy out there with cameras to film it.
Right.
So they were, on
And there was
target.
also some filming from like the very southern bits of Florida when it was coming back too, because
Oh, I
it
haven't
was in
seen
the
that.
Gulf.
Yeah, but yeah, the whole chopstick capturing thing. They have their launch tower, and it has these 2 arms that can spread out to about a 90-degree angle. And so because the Falcon 9 rockets, when they come back, they just come back and land on feet.
Right.
And they have to, land within an area of the size of a tennis court or something like that. This thing has to come down right next to the tower within the reach of these chopstick arms, has to hover there, then have the chopstick swing closed and grab it. Because it doesn't really have legs.
Can they put legs on it?
They're not going to. I mean,
I just feel like that would be easier, wouldn't it?
This is their architecture.
All right.
And then the upper stage is the big stainless steel Starship rocket.
So what's the over-under on this working the first time they try it?
Bringing it back to land, you mean?
Getting the chopsticks to work and actually...
Yeah. I
don't think it works the first time.
Yeah, what do you think is going to happen? Because they may well try it the next test.
I think they'll probably get close, but I think that then it'll fall over or...
Do you think the launch tower will survive?
I don't know if it'll be completely demolished, but I don't think it'll be usable.
Damage. Yeah.
For the next one.
But the heat shield thing was about Starship.
Yeah. So there's one of the cool thol about Starship. I don't like a lot of things. I'm just going to say it. It just frustrates me. I wish. Anyway, one of the cool things, though, is that when it's doing its thing and it's coming back in, it's got cameras on board, external cameras that are like imaging. And as it's coming in, it's got a heat shield, and you can see the plasma forming around it as it's igniting the atmosphere because of its motion. Yeah. And
nice.
It's super cool. And the reason, so usually when you have a rocket coming in, and it always creates that plasma, but usually you like completely lose comms and things like that because they have to communicate to the ground. But there's plasma between you and the ground, and plasma is ionized radiation, right? And so then you can't, or ionized atmosphere, and you can't communicate through that. It's not friendly with radio waves. But Starship goes back out to space to Starlink. And is able to send video. Right.
So you get live video. It's truly cool. It's stuff we've never seen before. And it looks
How do the
kind of amazing.
Survive?
Well,
they have some good housing. Yeah. And one of them got super coated with a bunch of crap from a fin that started burning up and disintegrating. And all that crap fell on the camera and coated it.
At one point you see the plasma punch a hole through one of the leading fins of the Starship, and then it's then you kind of the video kind of goes out, and then it comes back, and you can't really see what you're looking at. Then you can see it, and it's like this all torn up, mangled fin is still working. It's still steering the ship.
It's barely connected, but it's still working.
Yeah.
So the plasma stuff was really cool. And the heat shield did better this time. And I actually I don't think I ever actually saw the final landing for Starship. But
yeah, they didn't have that, I think, mapped out the same way they did for the booster, but I'm not sure. And then, of course, the next flight on a much smaller scale, which I alluded to earlier on June 8th, was the
Virgin
Galactic US VSS Unity flight.
Yeah, so this one and the previous one from Virgin sort of took us by surprise because they had been they did a flight a year ago or a little bit more than that, and they were now we're going to take a 2-year hiatus while we get our new line of spaceships on board. But then they've done 2 flights since then. Yeah. But this is probably actually the last one.
Yeah, their new
Unity.
Vehicle, I guess, is going to be
It's
bigger.
Called Delta.
Yeah.
Yeah.
And perhaps, I guess, carry more people. I don't
Probably.
know. And presumably have a more rapid turnaround. So Virgin Galactic's been struggling a little bit to get the whole commercial tourism thing really every weekly or daily flight kind of thing, which is sort of what they need for their huge backlog of customers to be able to
When was their last?
Their last flight was in January.
Yeah. So these two they did a pretty rapid succession in 2023. And then at the end of 2023 they were okay, we're going to stop for a couple years while we bring our Delta class online. But then they've done these 2 this year.
Okay.
So
anyway,
that's
space
our
flight.
space news update. Let's see. We have some astrophysical stuff. So let's let Jim transition us to that with his topical trivia.
Ooh. Okay. I'm excited.
Jim's excited to hear the trivia.
Because I could get it right today.
Oh.
This is going to be awesome. We're going to be talking about radioactivity.
Okay.
Specifically, I wrote some stuff down here on an actual piece of paper.
On a piece of paper.
On a piece of paper. Here, your question is going to be fairly simple. There are lots of isotopes of lots of elements out there in the universe that are unstable. They're radioactive. They decay if you just leave them there.
Yes.
So my question to you is, what is the time scale for the shortest reliably measured half-life of any radioactive isotope?
Oh, man.
And for the longest reliably measured radioactive half-life.
So it has to have been measured like in a lab or something.
So that is we have obviously you can, there are theoretical things like the proton might be unstable on time scales of whatever, some insane thing, but we've never seen a proton decay, so we have no reliable measurement of that or anything. But
we're talking about atomic nuclei
decaying and becoming
spitting out a neutron or splitting in two or whatever the case may be.
Something like that.
Okay. All right, we'll come back to that. Now,
everybody's so excited, Jim.
I was excited. I think
it'll be interesting.
Is our list of options the full periodic table?
No, you don't have to tell me the element. You have to tell me like what the time is. Like what is the longest measured?
I understand.
Like 1 minute.
And there are some elements that are only my question is whether this includes non-naturally occurring elements.
Oh.
It will include any
element that appears on the periodic table,
elements,
which we've made because their half-lives are so incredibly short that you never
find
them anywhere.
That's
sneaky.
That's right.
Okay. All right.
Yeah.
So, related to that, carbon is an element.
That's actually how I started looking at that. I was like, I'm going to make a question about carbon. I was like, carbon's too boring. Let's get nuts.
Let's look at big atoms.
Yeah. But carbon is interesting.
Carbon is also radioactive.
It is.
Yeah. Well,
everything is.
Many most elements have many isotopes, and some of those are pretty stable, and some of those are unstable. Carbon is, of course, one of them, and it's used, and notably, of course, to find out the age of a lot of things in biology and anthropology and stuff. The radioactive decay of carbon-14. But that's not what this is about. This is about carbon in the early universe. This is another thing that JWST has, of course, done a tremendous number of things for us, especially in astronomy associated with the very early universe, because that's what it's designed to do. To see.
Initially, you were like, JWST has done all sorts of things for us, especially associated with astronomy.
Fact.
In the early universe.
True. That is true.
In the early universe.
I was like, what has it done for me not in astronomy?
Yeah.
Oh, some
like
people might fight you because like planetary science stuff.
That's astronomy.
I know. Some people.
It's probably there's probably been some engineering things that came out of the design of it or something like that, but I don't know anything about that.
Yeah,
sure.
But yeah, early universe. This is looking at a galaxy that's only a few 100 million years after the Big Bang.
Just a little baby galaxy.
And yeah,
Josh is back on board now.
I'm saving my objection.
And finding that there's a lot more carbon in that galaxy than we had previously suspected was possible. Carbon, it turns out, we thought would take a long time to build up appreciable amounts.
You have to make it inside a star and blow up the star.
Yeah, that's right. And then, you have to do that a few times in order to build up some appreciable amount of it. And for reasons that are complicated and probably beyond me, oxygen tends to build up before carbon tends to build up. There's more oxygen in the universe than there is carbon.
That
tends to be
when
easier.
You think about it, somewhat surprising, I guess.
Yeah, I mean, it has to do with the particulars of what fusion reactions are happening in stars, and the specific reactions that are happening depend on not just the mass of the star, but the metallicity of the star. These, stars that are these very early stars, which we call population 3 stars, the very first stars in the universe, are doing fusion a little bit differently than our sun because they have zero
or zero,
anything other than hydrogen, helium in them, and so anyway, they tend to produce more oxygen than carbon, and so we expected to see like the ratios of carbon to oxygen to be more oxygen heavy, but we're seeing a whole bunch of carbon, which is, as JWST has routinely done, challenging our ideas about how things work in the early universe.
So my question, my objection, my query.
Here we go. You saved it.
How confident are we that these galaxies are only when the universe was 300 million years old or whatever?
This has been the big debate. Is like, how well are we timing these things?
Oh, yeah, no, that's a good question, because so the way we're determining how old they are is with redshift, of course. So we're measuring the redshift of these things, and then the good question that I think Josh is getting at is, what's the error bars on our redshifts? Because what's the difference between 200 million years after the Big Bang and 600 million years after the Big Bang, or something like that? I think it's...
What is the difference?
400 million years.
Thank you. All right.
But the difference, for something like that, the difference in redshift is actually quite a lot. Like the difference in a few hundred million years later in the universe
is nothing.
Is not very much in redshift. The difference in 400 million years in the early universe is a lot in redshift.
Right.
Yeah. And so I think the measurements of these redshifts are good enough that they've pinned it down to within 100 million years-ish.
If you're actually sure that what you are seeing, like I thought the issue with these measurements of early galaxies from JWST data was you're looking at a spectrum that I would only call a spectrum with air quotes around it. Not a lot of very clear, well-defined spectral features.
Right.
You kind of like find a feature and you assume that feature is like Lyman alpha emission from hydrogen.
Right.
And then you say, okay, if that's that, then the redshift is 10 or whatever.
Right.
And you get an age. But then some people are like, oh, but that could be some kind of absorption from dust somewhere between us and way back there, or something like that, that's doing something.
My understanding of this one was that they had reasonably clear, like, actually emission lines from carbon, which, again, I'm sure that there's conceivable ways you could screw that up. And
inconceivable.
But
I want that little clip. Like insert into the podcast.
Oh, that would be
once
nice.
We're fancy enough to do some audio engineering and we have like a button and we can insert sounds.
Inconceivable.
That you want that? You want that to be just like in our menu of things that we can insert from time to time?
Disc jockey.
Yeah.
The Addy inconceivable button. Okay.
Sorry to derail.
I'll process that.
Okay.
Process that.
I want that to be a sound clip too.
Josh gets tongue-tied.
So I mean, certainly,
universe.
I don't know enough about the data analysis to say.
Okay, that's fine.
I would certainly say that's a reasonable hypothesis that they've just done.
It is unreasonable. I don't know.
I don't do this kind of spectroscopy, but just looking at their figures, it looks pretty good to me. And
we're all peering at Audrey's computer, and it does look more spectra-y than some of the other early galaxy spectra that I've seen.
Yeah, and this is they observed with NIRSpec, the JWST NIRSpec
and that's one
instrument.
That we trust more now.
Yeah, and there's
see that Lyman alpha line there. That's
the
the thing that has been kind of like
fascinating radio.
Yeah.
Right. But this one's not measured just with that.
Josh is pointing to a plot that shows.
So anyway, I think I believe it. And I mean, it's not horribly surprising that our like understanding of how these elements build up at that time is a little off.
So how often? I mean, because the way we make carbon or oxygen, for that matter, is stars fuse hydrogen, helium. They make the heavier elements. They blow up, and happily for us, we owe our existence to it.
We're a big fan.
Bigger stars do that very quickly.
Right.
Mm-hmm.
They run through their fuel in a hurry and make a big boom. Mm-hmm. Which you will see on your little 2-minute journey.
She's so excited. Ooh, do you have special glasses on for this where you can like see in different wavelengths?
Yeah, I'm gonna have to.
Ooh, yeah. Can we have special equipment?
So you can see all the different.
But without the pain.
Yes. Oh, and then you could like flip through like different filters.
So badass. Oh yeah.
You record it.
Very excited.
Yeah. So you'll be able to see all that.
I want that on mine too.
So that kind of thing, one could imagine you would make a whole bunch of giant stars and they would burn out in 10 million years and so why is it just because somebody had done some calculations and said we'll get that much carbon in 500 million and here
yes I mean I think that the previous calculations they said it'd take about 1 billion years to build up the kind of amount of carbon that they're seeing here, and they're seeing it 300 million years after this, so this is it's
so that's an extra 700 million years for life to get a foothold.
Right. That's exactly one of
this
the
is kind of like what we were talking about with Venus last time, right? Where they were like, if we model things a little bit differently.
Oh, right, yeah.
I mean, we don't know how exactly all these physical processes happen because they're in such different physical conditions than what we're used to. So even our models sometimes you adjust it one way or the other, and you can add some more time.
It's funny because one of the articles about that had that life bit as one of the it's like
taglines,
as if that's probably not really what they're thinking about at all. You read the actual science paper, life doesn't come up at all. But
it's because it's astrophysics.
People like
cosmologists,
aliens,
carbon earlier.
Cosmologists aren't doing a lot of attendance at like AbSciCon or anything like that. Typically,
astrobiology
conference.
No.
So, and before you tell us about the shortest and the fastest and slowest radioactive decaying, we got an interesting story sent to us by a fan of the show.
Friend of the show, maybe?
Friend of the show.
Not a fan of the show?
I can't speak to that.
Friend of the show. There's
show.
a distinction, I guess, between fans of the show and friends of the show.
Mm-hmm.
Yeah. Friend of the show sent us an article about a new paper I think it's in Monthly Notices.
It is.
Which is a respectable scientific journal, but it's not the one where like the earth-shattering discoveries are published.
No.
And I can say that essentially I have some papers in those earth-shattering journals, but really not. Where somebody has come up with an alternative to dark matter.
Yeah.
What? Another one?
Well,
nice.
One of the things that's interesting about this is that it's a single author paper. And like in this day and age, there are still more theory papers that are single author papers because one can sit down with a piece of paper and like theorize about some stuff and be correct or not and like do some
write a program.
But the majority of papers these days are not single author papers. And it's because you have to work with a team or at least one other person and on things. Anyway, this is a single author paper, which is not to say that this person isn't a highly respected scientist.
No. I mean, I don't think there's any.
But it is one of those things where, like, okay, well,
there's nothing.
This is some theory.
To our knowledge, anything technically wrong with the paper, right?
No.
I mean,
it's a bit epicyclic.
So,
well, you got. I mean, I'll say some very positive things before we say any more negative things about it. I mean, dark matter is one of these things. Like, it is frustrating.
It is one of those things.
One of those things. Like, it is. Still our best explanation for all these weird phenomena that we see, the weird rotation of stars around galaxies and so forth. But we still have not found the smoking, and we have not found
a piece of it.
We haven't identified exactly what it is and found a piece of it, and that's it's frustrating. It's not necessarily surprising, but it's frustrating. And so it is very reasonable, and the scientifically correct thing to do is to look for alternatives.
Absolutely.
Right?
It's a laudable
And we
activity.
talk about a lot of ways, a lot of things people are proposing that have
absolutely.
been
The big alternative for a long time has been that modifying Newtonian physics, and that's, like I said, it's laudable to keep doing that.
Yeah, and not too long ago we talked about a version of that was tested that failed.
Right. That's how science should go, right?
Yeah.
You come up with many hypotheses and you test them, and if they fail. So here, this is, to give props to this guy, this is yet another different possible solution to this thing, and it's worth thinking about those things.
So walk me through it, because I didn't totally get it.
It involves
same.
It involves math and shells.
I did get that much out of it.
There are shells and shells.
Yeah.
Which is why I said it's epicyclic thing to me.
Sort
where
of like
it's like
those old
you
models.
need multiple things to explain the motion of one thing. Like epicycles were how we explained like
the
retrograde motion and the motion of the planets, where you had like multiple layered things together to like explain a relatively simple thing, but we didn't know about calculus yet, right?
Right.
And ellipses. So
yeah.
So maybe this is like sort of like that, where you're like, it's a way to sort of get toward an answer, but it's just a way to like explain the physics a little bit differently. With a different mathematics, right? Maybe we just can't explain it to get dark matter yet.
Well, this involves general relativity.
It involves general relativity, and just like math, it's like the there's the Poisson equation, is a famous equation in physics, and
and it's actually a fairly simple equation.
It's a fairly simple equation, and it's a Newtonian. I mean, it comes up in Newtonian gravity, Newtonian physics, and you solve it. So and it tells you things like if you have a massive sphere and you're outside of it, that the gravitational force will decay as 1/r², etc. So, but it turns out that there are ways that you can get gravitational forces with. There are other solutions to the Poisson equation which aren't necessarily physical. Anyway, we don't need to worry about the math. The thing is,
thank you.
There are ways that you can. Basically, the approach here was, I wonder if there's any other way I could get these objects to move the weird way that they're moving,
right?
Without
extra stuff, having
extra mass.
Yeah, because basically the dark matter hypothesis is because things are moving faster than 1/r² would predict. If all of the mass that's making stuff move, we can see it.
Right.
So if you put extra in, then 1/r² works fine.
Right.
Yeah.
So this is another way of saying, okay, can I do something that makes...
I wonder if I could get it to be 1/r or something like that instead of 1/r². And it turns out you can almost always do this, right? This is the great thing about Einstein's equation is whatever solution you want,
you can find
get
a
it.
way.
You can find a way to arrange things to get it.
Yeah.
Find actually infinite numbers of ways to arrange things to get it. And this is basically what Einstein has come up with, some very strange system where there are these concentric shells of positive and negative mass stuff.
This is the part where I was like, okay.
Yeah.
This is the frustrating part, because the author says at the very beginning he's kind of frustrated with the state of dark matter, that you can't find dark matter. And so the solution then seems to be a less well-motivated, even more ad hoc, bizarre thing that you can't even simply test for the existence of.
Yeah.
And so it really goes off the rails.
That's one of the things, if it had like been this cool model and then there's like, this is a thing where you can look for this and be like, I'm going to test this out of this model, then...
So frequently you'll hear stories about this or other kinds of like new scientific things. Like we've talked about the Alcubierre drive, which is a solution to general relativity that gives so-called warp drive. It's slower than the speed of light, but it's a theoretical framework where you move by bending space around your spaceship. And it always used to involve negative mass or something like that, right?
Yeah.
And then the stories that you hear about that, they're always like, there's nothing in Einstein's equations that prevents you from having negative mass. Well, there's nothing in any equation that prevents you from having negative mass, because every equation just has m, and it, of course, you can put a negative number in there.
Sure.
So that
I can do a lot of things in math.
Right. So it doesn't mean anything to say, oh, Einstein's equations don't prevent you from putting a negative mass in.
It's like one of those things. It's like you have to start making rules because people do dumb things. It's like, well, we didn't know we had to make that rule.
Right.
Einstein wasn't like, well, of course nobody's going to put negative mass in.
Right.
That's an unspoken rule.
Right. Exactly.
Yep.
Yeah. So, okay, cool.
But maybe it's a solution.
Anyway, it's cool. It's an interesting cool math trick and stuff like that. It probably has no bearing on
outside the box.
Really. I like it.
All right, let's get back inside the box with some radioactive.
All right, first
you don't want to be in a radioactive box.
If it's a slowly radioactive decaying thing, then you'll be okay.
I'm fine with that.
All right, do you want to start with fast or slow?
Yes.
Okay, we'll start with fast. What is
the shortest
measured half-life of any radioactive isotope? Bonus points if you tell me what the radioactive isotope is, but that's tough.
Okay. I'll just throw something out there. I don't even know. I'm going to 12.
I'm going to get the wrong order of magnitude, I feel like.
I'm certainly going to be the wrong order of magnitude.
Yeah.
Pico.
But okay, whoever's the closest to the order of magnitude wins the prize.
There are so many different orders of magnitude. I'm going with 10 to the minus 12
10 to the minus 12 seconds. Okay, I like it.
What's pico?
I think that is 10
10 minus 12.
All right. Well,
So
that's
you could
what
also do that.
Yeah.
Pico,
A
pico.
picosecond.
Okay, 10 to the minus 12.
I'm going to go 10 to the minus 14.
Whoa.
10 femtoseconds.
Femtosecond.
10
Is that
femto.
It's actually
Yeah.
it's hydrogen 5.
Oh, sure.
It's a weird
Okay.
Hydrogen 5?
hydrogen 5.
That sounds not real.
That does.
So it's certainly not
I
something
expected
you'll
it to
see in
be one
nature.
of those really high, made up
me
ones.
too.
Yeah.
Hydrogen 5 sounds like something that you would hear about in Doctor Who.
It's like Ice 5
Right.
or whatever.
Hey,
Ice 9.
you can slap
Yeah.
a pile of neutrons in anything. Anyway, hydrogen 5.
Apparently.
It has
Yeah,
a
I've seen
half-life
models for
of
it.
8.6 times 10 to the minus 23 seconds.
What?
and that's been measured.
That's
been measured.
measurable?
How has that been
It's been
measured?
reliably measured. That's by the way, that's 86 yoctoseconds,
Excuse you.
Yocto, I think.
Yocto.
That's also
spots-
from the Marx Brothers.
which is 10 to the minus 24. Right. All right, what's the longest one? Longest. How many?
10 to the
seconds?
24.
Oh, I like the
Seconds.
symmetry.
Yeah.
10 to the 24 seconds.
Yeah.
That's 10 to the 17 years, give or take.
Yeah. Give or take.
I think that's too big.
I mean, of course it is.
I'm gonna go. I'm gonna go with 10 to the 19 seconds.
10 to the 12 seconds.
All right, Addie wins this one. It's but she's still many orders of magnitude
Sure.
off.
Really?
It's
Somewhere between
69 giggity times 10 to the 30 seconds.
69 giggity times 10 to the 30 seconds?
That's not a
69.
number.
Giggity.
There you go. Parse it.
69 times 10 to the 30.
Man, Jim.
I got it. I'm there.
10
My,
times-
my race number for the running series for every race this year, and I got my name on the tag, 69. Joshua.
Nice.
Joshua 69.
And you have like 6 of those
I do.
So that's
for the upcoming
That, by the way,
series.
in-
Last year.
year's.
in the
See
metric
if you can do
prefix
that again
system,
this
that's
year.
69 quetaseconds.
What? Excuse you?
What?
In
How
2022,
Spell that? Can you use that in a sentence?
in 2022, they finally gave names to
10 to the...
10 to the 27 and 10 to the 30 and 10 to the minus
Oh,
27
that would be
and
a
10
fun
to the minus
trivia.
30.
Okay.
Yeah, those were good.
But now it's not because you're going to
Now
tell
I've
us.
ruined it. 10 to the
Well,
30
we'll all
is
forget.
Wait, what's a quetta?
Quetta. I don't know what the hell it comes from, but that's 10 to the 30.
Quetta.
Let me get back to the answer. How long is the element? How
Anna
long
Quetta.
is the half-life in years? Divided by 10 to the 7, roughly.
So it's 10 to the 30, so now it's 10 to the 23
23.
10 to
years.
the 23 years.
Which is
That's many years.
That
it's
is-
it's like 100
We're
trillion
gonna-
times the age of the
the
universe.
universe.
We're going to be on the podcast episode like 10 to the 23 by then.
And what is the
The element is tellurium 128.
It's not even, what? It's tellurium?
Tellurium. Xenon 124 is a close second to that. But
I
they're
want to
very long.
know how these things were measured.
Yeah, how was that one measured?
Oh.
Those are
You
really
just get a
tough because you
whole
are measuring.
bunch
You have
together?
a huge.
You have a huge number.
You have a huge number of them, and you're seeing a very
and you're
few
waiting
decays.
for one atom to decay.
Right. So with the Xenon 124,
wouldn't
they
trust
had this
that. I
whole
don't trust
thing full of Xenon, and they measured
Just
like
get a room
100
full of Xenon?
events in a year or something like that. And from that,
You
assuming
extrapolate.
that it
Right,
works like
yes.
every other radioactive
Sure.
decay, which it does, then you
Yes.
can figure out the half-life.
Yeah. Okay.
There's no negative mass.
No negative.
Well, while it may have felt like waiting for tellurium 128 to decay, it was just another episode of Walkabout the Galaxy.
Nice.
Give us 5 stars and we'll give you the universe.
Be sure to follow us on Facebook and Instagram to get all our updates.
Subscribe to our YouTube channel and catch up on old episodes wherever you get your podcasts.
Our theme music was composed by Richard Karusik.
You sure?
Production assistance is provided by Logan Basinger.
Thanks to our listeners in France and around the world. Stay safe. I'm Josh Caldwell.
I'm Addie Dove.
I'm Jim Cooney.
And I'm Audrey Martin.
We're the Astroquarks signing off until the next episode of Walkabout the Galaxy.
Apricots.
Nailed it! Bye.